Okay, let's get started. So good morning, everybody. Uh, Today's lecture is on limits of functions in two different ways. So first, one function, I'm taking a limit of x. This was technically listed as a last week topic, but I decided to cover it this Monday. So we'll start by that, a limit of a single function. And then I want to introduce two notions, pointwise and uniform continuity, and then draw an analogy between that and the main topic of this week, which is pointwise and uniform convergence of functions. And the main thing this week to understand is that there are two, the order of quantifiers matter, that for every x there exists a delta is a different statement that saying that there exists a delta such that for every x. We'll see this both in 2 and 3, and this will play a role throughout this week. So if you understand this difference, then you understand the topics of this week pretty well. So the difference between these, just to say that already at the beginning, is that here, for every x, there exists some delta. So this delta is allowed to depend on x. But the other way around, this is a uniform estimate. There is a single delta that works for all x. And you've seen this in 131a. It's exactly the same issue as with uniform continuity in that class. We'll just generalize those a little bit further and elaborate on this sequence of convergence of functions issue. Okay, so first, limit of functions. So this is you have a fixed function, and you're looking at what happens close by to a given point, x. So previously we had defined very similar notions. Well, we had defined a sequence of points. For every epsilon, there exists a capital N, such as blah, blah, blah. Then based on that, we can also define if we have a function that has x's in the domain, and the target is some metric space, we can talk about the limit along that sequence of a function, meaning we just take f of xn, which is now a new sequence in our target space, and we talk about it converging to something. But this doesn't really go much further than this. It's just a different sequence that you're applying to. So these notions talk about convergence along a particular sequence, the key word being a sequence. So here, we want to generalize limits to not talking about sequences in a similar way that we generalize continuity from sequential continuity to epsilon delta. So definition, if x0 is adherent to a set E, and if f is a function, this could only be defined on E, but because of how Terence-Tao defines things, this causes a little issue. So it has to be a function on all of x, even though we really only need some of the values. So technically it's enough that it's defined on E union x naught is enough. But okay, so but simpler to state for all, defined on all x. And then we define the limit as x approaches x naught in the metric space x. Now, this is a point approaching somehow this point x naught, but it can approach different ways. There's no fixed sequence, no fixed curve. We're talking about any way of approaching, really. So as x approaches x naught within the set E, our context, we say that fx approaches L, or the limit of fx is L, if for every epsilon there exists delta, such that if you're close enough in the space, your function value is close enough to L. And notice how this is not necessarily equal to f of x naught. Now, there's a small technical point here that you'll find differences in different books. I think the majority of books actually add a little thing here, bigger than or equal to 0. Terence-Tao does not do this. And the reason is that he has x0 adherent to E. Now, these are not a very different concept. The difference is basically what happens to the function value f of x naught if it is defined, and if x naught in E. So this limit point x naught could be in E, in which case this doesn't impose any condition on that point. So we should say here also the point x should be in E. And then talking about the limit point. Now, another difference, it's related to this point strictly bigger than 0, is about that many authors choose to define this for a limit point of E. And a limit point can be defined two different ways: that there exists a sequence that's not constant, such that the sequence xn converges to x naught, and in particular xn is not equal to x naught for all n, or the equivalently, that if you take a small ball, intersected it with E, that it's not just x naught for all radii. So the second is sometimes phrased as x naught not isolated. It's worth noting that Terence-Tao's definition has a little bit of a technical annoying thing, that, say, example of this definition, if you define any function, so if E is equal to, say, 0 union 1 2, and f of x, it can do anything really. It can be equal to 0 when x is equal to 0, and 1 when x is not equal to 0. Then limit as x approaches 0, x in E of f of x is just 0. This is an artifact of how Terence-Tao defines things. And why this is the case? Well, if delta is equal to 1/2, the only point y in, or x in E with distance from x to 0 being less than or equal to 1/2 is x equal to 0. So then automatically f of x minus f of 0 is less than whatever epsilon you want to give, because this is equal to 0. So kind of vacuously, unless at isolated points these limits exist and you can easily evaluate them as the function value, this is usually not desired, and this definition is more interesting if you have a limit point, so you can actually approach it without being a constant sequence. But Terence-Tao defines it this way, and it's quite, for some reasons, convenient. Now, this behaves like any limit. And just a small thing about notation, I don't like writing y in E all the time. So you can add it if you want. Otherwise, you can just assume y in x. These statements hold for both of these contexts, all of these statements. So you have the additive law: the limit of f plus g is equal to the limit of f plus limit of g, as long as the right-hand side exists. I mean, this is the same issue as in 131a. And in calculus as well. Same thing for products, ratios, but ratios, of course, you have to worry about the right-hand side not only existing, but being defined. So this limit at the bottom cannot equal 0. Now, and how this relates to continuity is that, actually this is an if and only if statement, goes both ways. The function f is continuous at a point x naught if and only if the limit as y approaches x naught of fy is equal to fx naught. I want to prove something about these, so I'll prove that continuity implies this fact. This fact is quite direct. So only for this direction, for proving. Okay, let's fix epsilon and let's assume that f is continuous at x naught. So this is our setup stage of the proof. We fix this notation. We want to show that limit y approaches x naught of fy is equal to f of x naught. It won't matter whether you add the f, y, and e for this statement. Let's do it now without it to simplify notation. So we want to show this. Well, we have fixed our epsilon to do that proof. So we need to find a delta that if you are that close, this function converges, function value is close to f of x naught. Well, where could we find it? Since f is continuous at x naught, there exists a delta such that if distance of y to x naught is less than or equal to delta, then distance fy to f of x naught is less than or equal to epsilon. This holds for every epsilon, so it holds in particular for the epsilon that we fixed in the beginning of the proof. So now we have to verify that the limit definition is satisfied with the same choice of delta. This delta is positive. We have the same implication, namely, let's not rewrite that. Same implication holds by the same choice of delta. And this is the definition. This is exactly what we needed to show for the fact that the limits of as y approaches x naught of fy is equal to f of x naught. Any questions? So it's very closely related to continuity. The difference between continuity and this limit definition is that here, this does not need to be equal to f of x naught. In fact, actually, if if x naught is in E, in Terence Tao's definition, it automatically has to be continuous at that point. But more generally, it doesn't need to be. But, okay, and now the main theorem that around this concept is that another way of characterizing, just like continuity, there's another way of characterizing this limit, and it's by sequences. So if you have a fixed point, x naught, then we could talk about some sequence converging to x naught. This is our yn, and we could ask, there should be L here. We could ask whether the limit as n goes to infinity of f of yn is equal to L. So this is for a particular sequence, a particular way of approaching that. See? But there are many sequences converging to x naught. So yn prime, yn triple prime, different ways of approaching. And the idea with this definition is that regardless of the way that we approach, we get the same value L. If this is true, so for any sequence approaching x naught, that we get the same value, then we say that this is the same thing as saying that the limit is equal to L. This is very analogous, and you should think about how sequential continuity is equivalent to the epsilon delta continuity. In fact, you can use this fact to prove that claim. Now, I'll go over the proof of this statement. One of these directions is fairly direct. It has direct proof from 1 to 2. If the limit is L, then the limit also is along any sequence. So let's suppose that one holds, and let's fix some epsilon for the limit proof, sequential limit proof. Let's fix a point x0, yn in E, so that yn approaches x0. And yn is in E, x0 has to be adherent to E to be a limit point. So we fix those. And what we want to show is that there exists some n such that f of yn minus f of x0 is less than or equal to epsilon for all n bigger than or equal to capital N. Because this means that the sequence converges. So we need to find that n. Well, how do we find that n? We have to first use 1 essentially. So by 1, because we are assuming that's the case, there exists a delta positive such that if distance x to x0 is at most delta, then distance between the function values is at most epsilon. So now we know that if the points are close, then the function values are close. And what we have to combine it with is that eventually the yns get close enough to x0. So let's find an n. Since limit n goes to infinity, yn is equal to x0, there exists an n such that if n is bigger than or equal to n, then distance yn to x0 is at most delta. So we are using delta instead of the usual epsilon as our variable. Now with the same choice, we have to verify that it works. If n is bigger than or equal to n, then distance yn to x0 is at most delta. This is by choice. And then by what we said here, by star, we know that distance of f of yn and f of x0 is at most epsilon. And this is exactly what we wanted to show. So it's really just reinterpreting the quantifiers. One is saying that if any point is close enough, then the function values is close. And this is saying if you're along the sequence, then that converges, then you get close. But of course, any sequence eventually is sufficiently close. So these are the same thing. Now, going the other way involves contradiction. So whereas one direction is easy, the other direction is by contradiction. And there's really no other way of doing this. You could write it as a contrapositive, but it's essentially the same. And the reason why you get contradiction here is for the same reason that for sequential continuity and epsilon delta that you need a contradiction proof. For the same reason that that occurs. So, well, we have to think, what is the negation? What is the negation of 1? So negation of 1, so we're assuming that 2 holds, that along any sequence we converge to L, but we want to then conclude that negation of 1 holds, or argue that contradiction ensues from that. So 1 states for every epsilon there exists a delta, so that the negation means that there exists an epsilon positive, such that for no matter the delta, then the tricky part here is how to contradict the implication, and many people make a mistake here, that if the distance, that there exists some y such that distance y is close to x0, but at the same time, the function value is far away. I mean, this is what it means for an implication to fail. The assumption is true, but the conclusion is false. So often people will write things like, this implies that, but that's not the negation and will lead to issues if you use that. Okay. So this being the negation, how do you use this to construct a bad sequence that contradicts 2? So bad means that contradicts 2. This is just a sketch of the argument. Well, it's a very common idea. If you have something for every delta, you apply it for different delta. So let's fix an epsilon so that star holds for every delta. Now star holds for delta equals 1 over n for any n natural number. This gives a sequence yn so that distance yn to x naught is at most 1 over n, because we're using the fact that this holds for every delta. In particular, it holds for delta 1 over n. And distance of fyn to f of x naught is big. It's bigger than or equal to epsilon. Sorry, it should be bigger than or equal to epsilon here. So you have these very close points that are mapped relatively far away. These are distance delta. On the image side, they are pushed further apart by the map path. Okay, so points close get mapped to far away. And we want to, where is the contradiction in this? Well, there are two statements here, A and B. Well, A, what it means is that limit and as n goes to infinity of yn is equal to x naught. Why is that? Because the distance is going to 0. You've seen this argument before when we talked about open sets and other conditions, which requires a short argument, but let's skip that now. So B means that you have a sequence conversion, but B says that the distance is always bigger than epsilon, so limit as n goes to infinity of f of yn cannot equal f of x naught. But this is a contradiction because the assumption is true, but the conclusion is not, so the implication fails. This is not, I didn't write all the details, but it's a sketch. So questions on this, anybody? Yes, so we need distance bigger than or equal to epsilon. So I said it incorrectly earlier that distance would be less than epsilon here. Distance needs to be bigger than or equal to epsilon. And let's just highlight why is this, just a little bit more detail to this. If limit n goes to infinity of fyn is equal to fx naught, then there would exists some capital N such that for all n bigger than or equal to capital N, distance of fyn to f of x naught would be less than epsilon, say less than epsilon over 2, but it's also always bigger than or equal to epsilon, and that's another way of writing this contradiction. Other questions, Devin or anybody else? So this is a common thing that comes up in many proofs, is that if you have the contradiction property, you use that to construct the sequence, and that sequence somehow doesn't fail some other property, and then you use these together to derive a contradiction. Okay, so that ends the discussion on limits of functions. Now